Right now, passing through the room you are lying in, there is light that should never have been able to reach you. It has been traveling for 13.8 billion years, and for much of that journey, it was moving away from you. Not because it slowed, but because the distance it had to cross was growing faster than light can cross it. The material that released it was receding from this exact spot at 58 times the speed of light. And it is not a special case. Nearly every object in every long-exposure photograph ever taken is receding from us faster than light tonight. About 97% of everything we can see, not approaching light speed, past it, 2 and 3 times over. Relativity is not broken, and this has been the standard position for a century, which leaves one question worth spending a night on. How can the universe expand faster than light? Get comfortable. Hit subscribe if you're new here, because by the end of tonight, you will have the exact answer, and it turns on a single word that was quietly dropped from the rule you were taught. Now, let's slowly ease into this. Part 1. The number that should not exist. There is a photograph you have almost certainly seen. It is one of the long-exposure images, the kind where a space telescope stares at a single small patch of apparently empty sky for hours or days at a time, and slowly accumulates the faintest light there is. The result looks like a scattering of jewels on black velvet, and every one of those smudges is a galaxy, and every one of those galaxies holds somewhere between a few billion and a few 100 billion stars. You have probably seen the caption underneath. It usually tells you how far away the objects are and how old the light is, and it usually leaves you with a pleasant sense of scale. Here is what the caption never says. The majority of the objects in that photograph are moving away from you faster than light. Not almost as fast as light. Not approaching the speed of light as a limit they can never quite touch. Faster. 2 times faster in some cases. 3 times faster for the oldest light we have. And they were moving away faster than light at the moment they emitted the very photons you are looking at. I want to be careful here, because this is the kind of sentence that usually comes with an escape hatch attached, and this one does not. This is not a claim about the far future. It is not a projection about what will happen billions of years from now. It is not a fringe theory, or a minority interpretation, or one cosmologist's provocative reading of the data. It is not a trick played by choosing a strange definition of the word distance in order to generate a headline. It is the standard model of cosmology, computed from parameters that have been measured to better than 1%, and it has been the mainstream position for very nearly 100 years. Georges Lemaitre had the structure of it in 1927. Arthur Eddington wrote it down plainly for a general audience in 1933, in a book he called The Expanding Universe, and treated it as unremarkable. Every graduate textbook in cosmology on the planet contains it. In 2004, 2 astronomers named Tamara Davis and Charles Lineweaver published a paper in the publications of the Astronomical Society of Australia titled Expanding Confusion. And the entire reason that paper exists is that professional textbooks and popular accounts kept getting this wrong in print, and somebody had to go through and list the errors. So the fact is not in dispute, and yet, sitting next to it, is another fact that you have heard even more often, and that is not in dispute either. Nothing can travel faster than light. That is the most famous rule in physics. It is more famous than any equation. It has been tested at particle accelerators, in atomic clocks flown around the world, in the timing of pulsars, in the arrival of neutrinos from a supernova in a neighboring galaxy, in the simultaneous detection of a gravitational wave and the gamma-ray burst that accompanied it. When physicists thought they had violated it, in 2011, with neutrinos apparently arriving 60 nanoseconds early at a detector in Italy, the result was retracted within months because a fiber optic cable had not been screwed in properly. The rule holds. It has never not held. Take those two statements and lay them next to each other. Nothing can travel faster than light. Most of the universe is receding from us faster than light. Both of them are true. Both of them are taught. Almost nobody who repeats them has ever noticed that, on their face, they cannot both be right. Let me give you the numbers, because the numbers are what make this stop feeling like wordplay. Astronomers measure the recession of a galaxy through its redshift, a stretching of the light on the way here, and they label it with the letter Z. A redshift of 1 means the light arrived with twice the wavelength it left with. The threshold you want is a redshift of about 1.5. Every object above that redshift is, right now, receding from us faster than light. That is not a rare category. The Sloan Digital Sky Survey alone catalogues hundreds of thousands of quasars above that threshold. Essentially, every galaxy that a space telescope has ever been pointed at in a long exposure is above it. The current record holder, a galaxy called Jade's GSZ 140, sits at a redshift of 14.32, and it is receding from us at 2.33 times the speed of light. The oldest light in existence, the microwave background that fills the sky in every direction and is passing through your body as you lie there, came from material that is now receding at 3.13 times the speed of light. And the engine that produces all of this is a single line of arithmetic, discovered a century ago, and simple enough to fit in a sentence. The rate at which a distant galaxy recedes from us is proportional to how far away it is. Double the distance, double the recession. That is the Hubble-Lemaitre law, and it is written as v equals h times d. Velocity equals a constant times distance. Look at what that shape commits you to. If recession grows in a straight line with distance, and there is no maximum distance, then there is no maximum recession. Somewhere out there is a distance at which the recession velocity, plugged into that formula, comes out exactly equal to the speed of light. That distance has a name, and it is called the Hubble radius, and it works out to about 14.5 billion light-years, and past it, the formula just keeps going. It does not flatten off. It does not develop a ceiling. It does not apologize. It gives you 2 times the speed of light, and 3 times, and it will give you 100 times if you feed it a large enough number. So the arithmetic is not hiding anything. The law says what it says. Which leaves exactly one question worth spending a night on. How can the universe expand faster than light? I am going to give you the complete answer tonight, and I want to be honest with you about the shape of what is coming, because the answer is not a loophole. It is not a technicality, and it is not a case of physicists quietly moving the goalposts when nobody was looking. The answer is that one of these two statements is not saying what you think it is saying, and once you see which one, and see exactly which word inside it is doing the work, the contradiction does not get resolved. It stops existing. It turns out never to have been a contradiction at all. But to get there, we have to take apart something you are carrying around in your head right now, something you almost certainly did not choose and have never examined. There is a picture of what the Big Bang was and what expansion is, and that picture is doing all of the damage. It is the reason this feels like a paradox. Nobody teaches it to you directly. You absorb it from documentaries and diagrams and the shape of the word itself, and then you carry it for the rest of your life without ever checking whether it is right. It is not right. And when it goes, the whole problem goes with it. We are going to go slowly. And we will start where everybody started, in a small observatory, on a hill in Arizona, with a man photographing smudges of light that nobody could yet identify, using a camera that had to be left open for entire nights at a time. Part 2. The Line Through the Scattered Points. In 1912, at the Lowell Observatory in Flagstaff, Arizona, a quiet and extraordinarily patient astronomer named Vesto Slipher pointed a 24-inch refractor at the Andromeda Nebula and left the shutter open. He was not looking for the expansion of the universe. Nobody was, because nobody knew there was one, and nobody was entirely sure what the spiral nebulae were. The dominant view held that they were clouds of gas somewhere inside our own galaxy, possibly solar systems in the process of forming. The question of whether anything existed outside the Milky Way was genuinely open and would not be settled for another decade. What Slipher was doing was spectroscopy. If you spread the light of an object into its component colors, you find dark lines where particular elements have absorbed particular wavelengths, and those lines sit at fixed, known places. If the object is moving toward you, the whole pattern shifts toward the blue. If it is moving away, it shifts toward the red. The size of the shift tells you the speed. It is the same effect that changes the pitch of a siren as an ambulance passes, applied to light instead of sound, and by 1912 it was a well-understood technique. The exposures took entire nights, sometimes several nights, stacked, because the nebulae were faint and the equipment was slow. When Slipher finally developed the plate for Andromeda and measured the shift, he got a number that he did not initially believe: 300 kilometers per second toward us. That was faster than anything anyone had ever measured in the sky. Stars moved at a few tens of kilometers per second. This thing was doing 10 times that, and it was doing it in the wrong direction for what would come later. He kept going. Over the following 5 years, Slipher accumulated spectra for 25 spiral nebulae, which was a heroic amount of work with the instruments available. By 1917, the pattern was clear enough to state: of the 25, 21 were receding. Some of them were receding at over 1,000 kilometers per second. Andromeda, the one that started it, remained one of the very few coming toward us, which we now know is because it is close enough to be gravitationally bound to us, and is going to collide with us in about 4 billion years. Slipher did not know what he had. He published the velocities. He noted that the recession seemed to be the general case, and there the observational side sat, for years, while the theoretical side worked on the problem from the opposite direction without ever quite meeting it. In 1917, the same year Slipher's list was taking shape, Albert Einstein applied his brand new theory of general relativity to the universe as a whole and immediately ran into trouble. The equations refused to sit still. A universe full of matter, under general relativity, wants to either collapse or expand. A static universe is not a stable solution, in the same way that a pencil balanced on its point is not a stable position. Einstein was certain the universe was static, because everybody was certain the universe was static, so he added a term to his equation specifically to hold it still. He called it the cosmological constant, and he spent much of the rest of his life regretting it. In 1922, a Russian mathematician and meteorologist named Alexander Friedmann published a paper in the Zeitschrift für Physik containing the expanding solutions to Einstein's equations. He was not making a claim about the real universe. He was doing mathematics, exploring what the equations permitted. Einstein initially responded in print that Friedmann had made an arithmetic error, then withdrew the objection and conceded the solutions were valid, but described them as being of no physical significance. Friedmann died of typhoid in 1925 at the age of 37 and never learned that he had written down the future of cosmology. Then, in 1927, a Belgian priest and physicist named Georges Lemaitre put the two halves together. He derived the expanding solution independently. He connected it to the observed recession velocities that Slipher and others had accumulated, and he did something neither of them had done. He extracted a rate. He calculated how much recession you get per unit of distance, and the number he arrived at was around 625 kilometers per second per megaparsec. He published it in the Annales de la Société Scientifique de Bruxelles, which was, to put it gently, not a journal that the international astronomical community read. The paper sat there, largely unnoticed, for 4 years. When it was finally translated into English and published in the monthly notices of the Royal Astronomical Society in 1931, the paragraph containing the rate was gone. For decades afterward, this was treated as one of the great injustices in the history of science, a suggestion that somebody had suppressed a priest's priority claim. The truth turned out to be simpler and rather more human. Lemaitre had done the translation himself, and he had removed the paragraph on purpose, because by 1931, much better data existed, and he did not think his own preliminary number was worth reprinting. That better data came from Edwin Hubble, and it came from a telescope and a working relationship worth pausing on. In April of 1920, 2 astronomers named Harlow Shapley and Heber Curtis had stood up at the Smithsonian in Washington and argued in public about whether the spiral nebulae were inside the Milky Way or were separate galaxies of their own. It became known as the Great Debate, and it settled nothing, because neither side had the distances. 3 years later, Hubble, using the 100-inch telescope on Mount Wilson, found a Cepheid variable star in the Andromeda Nebula, measured its period, converted that to a brightness, compared the brightness to how faint it actually looked, and got a distance far outside our own galaxy. He wrote the letters VAR and an exclamation mark on the photographic plate. The universe acquired other galaxies that night. Much of the spectroscopic work that followed was not done by Hubble at all. It was done by Milton Humason, who had arrived at Mount Wilson as a mule driver hauling equipment up the mountain during construction, then took a job as a janitor, then as a night assistant, and turned out to be one of the finest observers of his generation, despite having left school at 14. Humason took the exposures that filled in Hubble's plot, sitting in an unheated cage at the top of the telescope through long winter nights. In 1929, Hubble published a 2-page paper in the Proceedings of the National Academy of Sciences with a plot in it. On the horizontal axis, distance. On the vertical axis, velocity. 24 galaxies, and the points were scattered, genuinely scattered, with a spread you would not accept in a modern undergraduate laboratory report. But there was a line through them. The further away, the faster the recession. Hubble drew the line and measured its slope and got about 500 kilometers per second per megaparsec. That number was wrong. It was wrong by roughly a factor of 7, and the error had immediate and awkward consequences, because the slope of that line is not just a rate. It is also, when you invert it, an age. If everything is flying apart at a known rate, you can wind the film backwards and ask how long ago everything was on top of everything else. A slope of 500 implies an expansion age of about 2 billion years. Geologists at the time were dating rocks by radioactive decay and getting terrestrial ages considerably older than that. The Earth appeared to be older than the universe. This was known as the age crisis, and it was a serious embarrassment that persisted for over 2 decades. It was finally resolved in 1952, when Walter Bard, using the 200-inch telescope at Palomar during the wartime blackouts over Los Angeles, realized that there are 2 distinct populations of Cepheid variable stars with 2 different brightness relationships, and that the distance calibration had been built on a confusion between them. Correcting it roughly halved the Hubble constant overnight. Alan Sandage's subsequent work brought it down further still, and the modern value is somewhere between 67 and 73, which we will come back to, because that disagreement matters enormously for tonight. Hubble himself, for the record, never fully accepted that the redshifts were velocities. He wrote about the apparent velocity-displacement relation, keeping the word apparent in place, and he continued to entertain non-expansion explanations into the 1930s and beyond. The man whose name is on the expansion of the universe was, to the end, professionally unconvinced. But here is the thing to hold on to from all of this, and it is not the value of the constant. It is the shape of the relationship. Velocity proportional to distance. A straight line through the origin. That is what Slipher's plates and Hubble's plot and Lemaitre's derivation all converge on, and it is the only ingredient the paradox needs. Because a straight line does not stop, and nobody in 1929 was asking what that line predicts when you extend it far enough, for the simple reason that nobody could see far enough for it to matter. We can, now. Part 3. The explosion, stated in full. I want to describe a picture to you now, and I want to do it properly, without any winking or hedging or telegraphing that it is about to be knocked down. This is the picture almost everyone carries. You did not choose it, and nobody sat you down and taught it to you. It assembled itself in your head, out of documentary graphics and textbook diagrams, and the shape of two words that were chosen, as it happens, by somebody who was trying to make the idea sound ridiculous. Here it is. In the beginning, everything that exists was gathered into a single point. All the matter, all the energy, every atom that would ever become a star or a planet or a person, compressed into something smaller than anything you can picture, and then it exploded. It blew apart with a violence that has no comparison, and the fragments went hurtling outward in every direction, and they are still hurtling outward now, 13.8 billion years later, slowly cooling and spreading and thinning as they go. The galaxies are the shrapnel. We are riding on a piece of it. That is the Big Bang, as most people understand it. And I want to point out something about it before we go any further, which is that it does a genuinely good job of explaining the data. Think about what happens after an explosion. Every fragment gets a different speed, at random, depending on how the blast happened to catch it. Now wait a while. Where are the fast fragments? They are far away, because they have had the same amount of time as everybody else, and they have covered more ground. Where are the slow ones? Still close to the middle. So if you stand at the site of the explosion afterwards and measure the debris, you will find that the further away a piece is, the faster it is receding from you. Distance and velocity will be proportional. You will get a straight line through the origin. You will get Hubble's law. That is why this picture is so difficult to dislodge. It is not stupid, and it is not lazy. It reproduces the single most important observation in cosmology as an automatic consequence, without needing anything else added to it. If you had never heard of general relativity, and somebody showed you Hubble's plot and asked you to explain it, this is the explanation you would invent, and you would be pleased with yourself, and you would be right to be. The name did not help. In 1949, the British astronomer Fred Hoyle was giving a series of radio talks on the BBC, and he needed a way to describe the model he disagreed with. Hoyle was a proponent of the steady-state theory, which held that the universe had no beginning and that new matter was continuously created to fill the gaps as things spread out. He was arguing against the idea of a moment of origin, and in the course of the broadcast, he referred to it as this Big Bang idea. The name stuck. It stuck so thoroughly that in 1993, a magazine ran a competition to replace it with something better, received more than 13,000 entries, and the judges concluded that none of them were an improvement. Hoyle himself spent decades insisting he had not meant it as mockery, that it was simply a vivid phrase for radio. Either way, the damage was done. 2 syllables of onomatopoeia, and an entire species now pictures a detonation. Hoyle's own model, for what it is worth, did not survive. The steady-state theory made a prediction that could be checked. If the universe looks the same at all times, then the population of radio galaxies at great distance should look like the population nearby. Radio surveys through the 1950s and early 60s found that it does not. There were far more faint sources than the model allowed, meaning the distant past was different from the present. And then, in 1964, two engineers at Bell Labs in New Jersey found a persistent hiss in a horn antenna that they could not eliminate, and it turned out to be the cooled remnant of the hot early universe, filling the sky, exactly as a model, with a beginning required, and a model without one forbade. Hoyle lost. His phrase won anyway. And it kept winning, in places where it should have known better. Physicists themselves use the language. Papers describe matter being flung outward. Museum exhibits show a bright point with arrows radiating from it. Planetarium shows begin with a flash. Every one of those is teaching the picture that generates the paradox, to people who will carry it for 50 years. So let us be precise about what this picture actually commits you to, because it is not one assumption, it is three, and they are all hiding inside the word explosion, and you have never had to say any of them out loud. The first is that there is a center. An explosion has a place where it happened. There is a point in space that everything came from, and that point still exists, and in principle you could go and stand on it. Somewhere out there is a location that is the middle of the universe, and we are some distance from it. The second is that there is an edge. The debris has spread outward for 13.8 billion years, which means it has reached a certain distance, and no further. There is a leading edge of matter, a shell, a frontier where the outermost galaxies are, and beyond that shell there is nothing yet. The third is the one nobody ever says, and it is the most important. It is that there is an outside. Space was already there before the explosion happened, a pre-existing arena, empty and waiting, and the explosion took place in it, and the debris has been flying through it ever since. Space is the room. Matter is the furniture. The furniture is being thrown around, and the room is unaffected. Hold those three together, and now put the observation next to them. If the galaxies are fragments flying through pre-existing space, then their recession velocities are velocities in the ordinary sense. They are speeds through the arena, exactly the kind of thing a speedometer would measure, exactly the kind of thing that special relativity was written about. And a galaxy receding at 2.33 times the speed of light is a fragment traveling through space at 2.33 times the speed of light. There is no interpretation available. There is no subtlety to appeal to. That is a naked violation of the most tested rule in physics, happening in the majority of every long-exposure photograph ever taken, in plain sight, and either relativity is wrong or the observations are wrong. I want you to sit with that for a moment, because this is the honest state of the problem. Inside the explosion picture, the paradox is not a confusion. It is not a matter of not having thought it through carefully enough. It is a flat contradiction, and if the picture were correct, then something enormous would be broken. The picture is not correct, not slightly off, not a useful approximation that breaks down at the extremes. Every single one of those three commitments, the center, the edge, the outside, is measurably, demonstrably false, and we have known that they are false for a very long time. And what is strange, and what makes this worth an evening, is that when they go, the paradox does not survive them. It is not that we find a clever way to allow galaxies to break the speed limit. It is that we discover the thing we were worried about was never happening. So let us take the three of them apart, one at a time, starting with the middle. Part 4. Where the picture breaks. Start with the center, because it is the easiest to kill, and you can do it with nothing but arithmetic. Imagine three galaxies in a straight line. Call them A, B, and C, evenly spaced, with 100 million light-years between each neighboring pair. Now let the whole arrangement expand, so that after some interval, every gap has doubled. The distance from A to B was 100 million light-years, and is now 200 million. The distance from B to C was 100 million, and is now 200 million. But the distance from A to C was 200 million, and it is now 400 million. Look at what that means from B's point of view. A has moved 100 million light-years away. C has moved 100 million light-years away. Both neighbors receding, at the same speed, in opposite directions. B concludes it is at the center. Now look from A. B has receded by 100 million. C has receded by 200 million, in the same time. So from A, the further object is receding twice as fast. Velocity proportional to distance. Hubble's law, exactly, measured by an observer who is not at the middle of anything, because there is no middle. And A also concludes it is at the center, because everything is running away from it too. Every observer, at every galaxy, in every part of the universe, measures the same law with the same constant, and finds themselves apparently at the middle of the recession. That is not a coincidence, and it is not a strange symmetry that needs explaining. It is what you get when there is no center at all. An explosion has a middle by definition, and the middle is a special place, and observers at different distances from it see different things. Nobody in this universe sees anything different. The pattern is the same everywhere, which means it has no origin point. Now take the edge. If we were sitting somewhere, inside a shell of expanding debris, the sky would tell us. Look toward the middle, and you would see a great deal of material. Look outward toward the frontier, and you would see it thin out and stop. There would be a direction that was different. There would be a gradient. And the further we happened to be from the center, the more lopsided the sky would look. The sky is not lopsided. The single most precise measurement in all of cosmology is the temperature of the microwave background, and it is the same in every direction to about 1 part in 100,000. Not approximately the same, not the same to within the errors of a crude instrument. The same to 5 decimal places, everywhere you point, over the entire sphere. Once you subtract out our own motion, which produces a small dipole, because we are drifting at 370 kilometers per second with respect to that radiation, what is left is a sky of extraordinary evenness. There is no thick direction and no thin direction. There is no frontier, there is no shell. And then there is the third one, the outside, which is the assumption nobody ever says out loud. This is where people reach for the balloon. You have seen the demonstration. Draw dots on a balloon. Inflate it. Watch every dot move away from every other dot. Notice that no dot is the center, and the surface has no edge. It is a good analogy, and it does real work. It gets you the centerlessness and the edgelessness in about 4 seconds. But it lies about one thing, and the lie is precisely the thing we need. The balloon has an inside. It has a room around it. It is embedded in the 3-dimensional space of the room you are sitting in, and when it inflates into that room. So the analogy quietly smuggles back in exactly the assumption we are trying to remove. The raisin bread version has the same problem. The loaf has a crust, and the crust is in an oven. In the actual universe, there is no room. There is no outside for the surface to be embedded in. When cosmologists talk about the universe expanding, they are not describing an object getting bigger inside a container. They are describing a change in the relationship between points, a change in how much distance there is between things, measured by rulers that are themselves inside the situation. The geometry is not doing something in a space. The geometry is the space. There is a consequence of this that is worth 1 paragraph, because it does something useful to the intuition. If there is no center and no outside, then the beginning was not an event at a location. It was a condition of everything at once. The hot, dense state was not somewhere else, far away, in a direction you could point at. It was here. It was at the coordinates you are currently occupying, and at every other set of coordinates simultaneously. The room you are lying in was part of it. The material that became the atoms in your body was in it, at 10 billion degrees, everywhere. When the universe cooled enough for light to travel freely, 380,000 years in, That happened here too, at your address, and the light released at your address that day is now 13.8 billion light-years away and arriving at somebody else. The oldest light you can detect tonight was released at a place that is now on the far edge of everything we can see, and it has been traveling toward you ever since. Which brings us to the sentence that this whole part has been building toward, and I want to say it as plainly as I can, because everything from here depends on it. Nobody is moving. The galaxies are not traveling. They are not journeying anywhere. A galaxy at a redshift of 2 is not, in any meaningful sense, going somewhere. It is sitting exactly where it has always been, doing nothing, surrounded by its own quiet neighborhood of stars, with no wind in its face, and no sense whatsoever that anything is happening to it. What changes is the amount of distance between it and us. The galaxies are not moving apart. The apart is increasing. If that sounds like a distinction without a difference, here is the test that shows it is not. Expansion does not act on things. It is not a force, and it does not pull. Consider Andromeda, the galaxy Slipher started with. It sits 2.5 million light-years away, and at that distance, the Hubble law predicts a recession of about 50 kilometers per second. Andromeda is not receding at 50 kilometers per second. It is approaching at roughly 110 kilometers per second relative to the center of our galaxy, and in about 4 billion years, it is going to arrive. Gravity has a hold on it, and once gravity has a hold, expansion simply stops being a factor, not reduced, not partially overcome, absent. The same is true all the way down. Your body is not expanding. The atoms in your hand are held together by electromagnetic forces that are not in a tug-of-war with cosmic expansion. There is nothing to be in a tug-of-war with. The Earth is not slowly drifting away from the Sun because space is growing between them. The solar system is not expanding. The Milky Way is not expanding. The local group of galaxies is gravitationally bound and will never expand. It will do the opposite and merge into one object. Where does expansion start to matter? Roughly above 100 megaparsecs, which is about 300 million light-years, because that is the scale above which the universe becomes genuinely smooth and the idea of an average density starts to mean something. Below that, structure wins. The Laniakea supercluster, the enormous assembly of galaxies we belong to, is not bound, and it will be pulled apart. The local group is bound, and it will not. So expansion is not a wind. It has no grip. It does not push anything, and nothing is riding it. Which leaves us in an odd position. We have taken away the center, taken away the edge, taken away the outside, taken away the motion, and taken away the force. Every ingredient the paradox needed is gone. And yet the number is still there. The recession velocity of that galaxy at redshift 14 is still 2.33 times the speed of light. Removing the explosion picture did not remove the arithmetic. Something is still being compared to the speed of light, and it is still winning. So what, exactly, is that number? Part 5. The word is local. Let us go back and read the rule properly, because I think you will find you have never actually seen it stated in full. The version everybody knows is, nothing can travel faster than light. 6 words, clean, memorable, and incomplete, in a way that turns out to matter more than anything else in this story. The version relativity actually gives you is longer and considerably more careful. It says that if 2 objects are at the same event, the same place, at the same moment, then the relative speed of one with respect to the other cannot equal or exceed the speed of light. If one of them is a photon and the other is you, the photon wins, and it wins by exactly the same margin no matter how fast you were already going. If both are massive, neither can be accelerated through the boundary, because the energy required climbs without limit as you approach it. Notice what that statement is about. It is about a comparison between two things that are in the same place. Every experimental confirmation of the speed limit has that structure. A particle in an accelerator and the detector wall it hits are in the same place. A photon and the clock that registers it are in the same place. A neutrino from a supernova and the tank of fluid in Japan that catches it are, at the moment of the measurement, in the same place. The rule is a statement about what can happen at a point. Physicists call it a local statement, and that word, local, is not decoration. It is not a hedge that got added later to make room for an awkward result. It is the entire content of the rule, and it has been there from the beginning, and almost nobody says it out loud when they teach the 6-word version. Here is why the word has to be there. General relativity is a theory of curved spacetime, and the founding structural fact about curved spacetime is that it looks flat if you look at a small enough piece of it. This is not a physics idea originally, it is a geometry idea, and you already know it. The surface of the Earth is curved, but the floor of your room is, for all practical purposes, a plane. Take a small enough patch of any smooth, curved surface, and it becomes indistinguishable from flat. Space-time works the same way. Around any event, if you zoom in far enough, the curvature becomes negligible, and the geometry becomes the flat geometry of special relativity, exactly. So special relativity is not wrong in a curved universe. It is exactly right, everywhere, in every small patch. Physicists say that general relativity is locally Lorentzian, which is the technical way of saying that the old theory survives intact inside every neighborhood. The speed limit lives in those neighborhoods. Inside every one of them, the light cone does its job, and nothing material gets outside it. Now, try to ask the question the paradox wants you to ask. How fast is that galaxy moving relative to me? To answer that, you would need to take the galaxy's velocity, an arrow pointing in a direction with a length, and bring it here so you could lay it alongside your own and compare. And in flat space, that is trivial. You slide the arrow over, keeping it parallel to itself, and you compare. Everybody has done this with vectors on paper. In curved space, it does not work, and the failure is not a technical inconvenience. It is fundamental. When you carry a vector across a curved surface, keeping it as parallel to itself as the geometry allows, the direction it ends up pointing depends on the route you took. Take one path, and you get one answer. Take a different path between the same 2 points, and you get a different answer. You can demonstrate this on a globe with a pencil in about a minute, and the disagreement is not small, which means the question has no unique answer. Not an answer we have not measured yet. Not an answer that is hard to compute. There is no fact of the matter about the relative velocity of two objects at widely separated points in a curved spacetime, because the comparison that the question presupposes cannot be performed unambiguously. The question sounds perfectly well formed in English, and is not well formed in the physics. So what is the recession velocity then? It is real, it is calculable, and people quote it constantly, so it has to be something. It is this. You take space-time and you slice it into moments, surfaces of constant cosmic time, defined by the clocks of observers who see the universe as evenly distributed around them. Then, within one of those slices, you measure the distance from here to a distant galaxy by laying rulers, end to end, along the slice. Then you do it again a moment later. Then you ask how much that number changed. That rate of change is the recession velocity. It is a legitimate quantity. It is not made up. But look at what it is. It is the rate at which a sum changes. It is the rate of growth of a total assembled out of many small pieces, none of which belongs to any single observer. Let me put you inside that, because it is the moment the whole thing becomes obvious. Imagine a line of observers stretching away from you, across 1 billion light-years. Each one is a few million light-years from the next, and there are hundreds of them. Every single one of them is at rest. Not approximately at rest. Genuinely, in every way any of them can measure. Each one looks at the stars in their own neighborhood and sees nothing streaming past. Each one has a clock and a ruler and a light source, and every experiment they run gives exactly the results relativity says it should. Nobody anywhere in that line is doing anything unusual. Now start walking. You ask the first observer, the nearest one, how fast the two of you are drifting apart. They give you a number, and it is small and entirely unalarming, a few tens of kilometers per second, the sort of speed a spacecraft manages. You move to their position and ask the same question of the next one along. Same answer, small, unremarkable, nothing happening. You keep going, observer to observer, along the whole chain, and at every single link, the two people involved would swear, correctly, that nothing in their vicinity is moving at any interesting speed at all. Not one of them sees anything approaching light speed. Not one of them sees anything they would describe as motion. Now get to the far end and add up every one of those small, boring numbers. The total exceeds the speed of light. And nothing happened. That is what I want you to feel. There is no moment along that chain where something crossed a threshold, no link where the physics went strange, no observer who witnessed anything. The number at the end is a sum, and a sum is not something that anybody did. You already accept this logic in a smaller form, and you have never noticed. Two cars drive away from each other, each doing 60 miles an hour. The gap between them opens at 120 miles an hour. No speed limit has been broken, no police officer has anything to write down, because 120 is not anybody's speed. It is the rate of change of a gap. Recession velocity is the same category of thing, taken to a scale where the sum can be arbitrarily large. Or take a laser pointer and sweep it across the face of the moon. Flick your wrist fast enough, and the bright spot travels across the lunar surface faster than light. It genuinely does, and nothing has been violated, because the spot is not an object, and nothing is being carried along with it. No photon traveled sideways. Each photon went out in a straight line at exactly c, and the pattern they landed in swept across the ground. Speeds like that are not velocities of anything. It is worth saying that the smallness of those local numbers is measured, not assumed. Galaxies do have genuine motion of their own, on top of the expansion, and astronomers call it peculiar velocity, which is a slightly unfortunate name for something that just means real movement through your own neighborhood. It is small. Our own galaxy's motion with respect to the microwave background is 369.82 kilometers per second, plus or minus about a tenth, which sounds enormous until you notice it is about 1/10% of the speed of light. Galaxies orbiting inside rich clusters manage a few hundred up to perhaps 1,500 kilometers per second. That is the fastest anything in the catalogue is actually going, in the sense that a speedometer would register it. Nothing anywhere in the observable universe has a local velocity that comes within 3 orders of magnitude of the limit. Every galaxy in existence is sitting comfortably inside its own light cone, and always has been. So let us list, precisely, what relativity forbids. It forbids 2 objects at the same event having a relative speed of c or more. It forbids accelerating anything with mass through the boundary in any local frame. And it forbids sending information or any causal influence between 2 events that are separated in a space-like way. Cosmic expansion does none of these. No galaxy ever passes a photon. No photon is ever overtaken. Nothing is accelerated through anything. And information does not travel between superluminally receding regions. In fact, the opposite is happening, and they are losing contact with each other, which we will get to before the end. The rule is intact. It was never threatened. But now we have a different problem, because if that number is not a velocity, We still have to explain how big it gets, and where it starts, and what happens at the boundary. And that boundary has a name, and a size, and a location, and almost nobody has heard of it. Part 6. The sphere nobody told you about. There is a boundary around you right now. It is centered on you. It is perfectly spherical. It is about 14.5 billion light-years in radius, and it is called the Hubble sphere. It is one of the most important structures in cosmology, and one of the least known outside the field. And almost everything people get wrong about tonight's question is a misunderstanding of what it is. Its size comes straight out of the law we have already got. Recession velocity equals the Hubble constant times distance. Set the recession velocity equal to the speed of light and solve for distance, and you get the speed of light divided by the Hubble constant. That is it. That is the whole derivation, and you could do it on the back of a receipt. Now we need a number for the constant, and here the story takes a turn that I did not expect the first time I looked into it, because we do not have one. We have two, and they disagree, and the disagreement is one of the sharpest open problems in physics. The first comes from the microwave background. You take the pattern of hot and cold spots in the oldest light, you fit it with the standard 6-parameter model of cosmology, and you read off the expansion rate. The Planck satellite's final analysis, published in 2018, gives 67.4 kilometers per second per megaparsec, plus or minus half a unit. That is an early universe measurement, made by modeling what the universe looked like when it was 380,000 years old, and extrapolating forward. The second comes from the ladder. You measure the distance to nearby stars by parallax, use those to calibrate Cepheid variable stars, use Cepheids to calibrate type Ia supernovae in galaxies close enough to contain both, and then use supernovae to reach far enough out that the expansion dominates. Every rung is calibrated on the one below it, which is why it is called a ladder. The SHOES collaboration, led by Adam Rees, published their result in 2022 in the Astrophysical Journal Letters, built on 3,130 individual Cepheid measurements across 40 galaxies. They get 73.04, plus or minus about 1. 67.4 and 73.04. Those two numbers, with those two error bars, are incompatible at about 5 sigma, which is the threshold particle physicists use to declare a discovery. This is the Hubble tension. It has been getting worse, not better, for over a decade. Every obvious explanation has been checked and eliminated. When people suggested that crowding in the Cepheid photometry was the culprit, that Hubble Space Telescope images were too blurry to separate Cepheids from their neighbors, UST went and looked at the same stars with sharper optics and ruled that explanation out at 8 sigma. The Chicago Carnegie Hubble program, led by Wendy Friedman, has been running an independent set of ladders using JJ West and 3 different distance indicators, the tip of the red giant branch, a population of carbon stars called the J region asymptotic giant branch, and Cepheids. Their status report, published in the Astrophysical Journal in 2025, gives a combined value of 69.96, with statistical and systematic uncertainties of about 1 each. Their JWST only tip of the red giant branch figure is 68.81, and their JWST only carbon star figure is 67.80. Those sit between the two poles, and their authors argue that no new physics is required. Not everyone agrees. There are other roots to the number, and they do not settle it either. Gravitationally lensed quasars give you a measurement with no ladder at all. A distant quasar flickers. The flicker arrives along several different light paths, bent around a foreground galaxy. The paths have different lengths, and the delay between the arrivals encodes the expansion rate. That method lands near 73, but the answer shifts by several units depending on what you assume about the mass distribution of the lens. Gravitational wave sources give you a fourth route, entirely independent of light. The waveform of a merger tells you the intrinsic loudness, the observed loudness tells you the distance, and the redshift of the host galaxy does the rest. The single event in 2017, with an identified host, gave 70 plus 12 minus 8. It will take many more before that method can arbitrate anything. Now bring that back to the boundary. If the constant is 67.4, the Hubble sphere has a radius of 4,448 megaparsecs, which is 14.51 billion light-years. If the constant is 73, the radius is about 13.4 billion light-years. The line past which the universe recedes faster than light is uncertain, right now, by roughly a billion light-years. And it is uncertain not because our instruments are crude, but because two extremely careful methods insist on different answers. Let me give you the ladder of recession velocities, computed with the Planck value, so you can feel the shape of it. At a redshift of 1/2, an object is 6.36 billion light-years away and receding at 44% of the speed of light. At a redshift of 1, it is 11.09 billion light-years away, receding at 76%. At a redshift of 1.46, it is 14.37 billion light-years away and receding at almost exactly the speed of light. That is the crossing point. At a redshift of 2, 17.3 billion light-years, 1.19 times light speed. At a redshift of 6, 27.5 billion light-years, 1.89 times. At a redshift of 10, 31.4 billion light-years, 2.17 times. At 14.32, the current record, 33.8 billion light-years, 2.33 times. The microwave background, at a redshift of 1090, sits at 45.44 billion light-years and recedes at 3.13 times the speed of light. And the particle horizon, the furthest co-moving distance light could possibly have crossed since the beginning, is at 46.5 billion light-years and recedes at 3.20 times light speed. So the answer to how much of the observable universe is beyond the Hubble sphere is almost all of it. 14.5 billion light-years out of 46.5 in radius. Volume goes as the cube of the radius, so the region where recession is subluminal is about 3% of the whole. 97% of what you can see is receding faster than light. That is not the exotic edge case. That is the normal condition of the universe. Now, two things about this boundary that you need before we go on, because they are where the confusion breeds. The first is that nothing happens there. There is no surface. There is no shell of anything. No change in the density of galaxies. No shimmer. No discontinuity in the physics. If you were somehow transported to a point on your own Hubble sphere, you would find a completely ordinary region of the universe with a completely ordinary region of galaxies in it. And you would draw your own Hubble sphere around yourself, 14.5 billion light-years out, and it would enclose the Earth. It is a bookkeeping radius. It is the answer to an arithmetic question about a formula, and it has no local existence at all. The second thing is the one that gets confused in print constantly, including in professional textbooks, and it is the reason the Davis and Lineweaver paper had to be written. The Hubble sphere is not the event horizon. They are different objects with different sizes and completely different meanings. We will do the event horizon properly at the end of tonight, because it is where this story actually goes. For now, hold on to just this. The Hubble sphere is the place where recession velocity hits the speed of light, and it is not a wall, and it is not the edge of what we can see, and things cross it. There is one more small thing worth noticing about the Hubble constant, which is that it is not really a constant, and its units are hiding something. Kilometers per second per megaparsec looks like a speed divided by a distance, and a speed divided by a distance is just an inverse time. Invert the Hubble constant, and you get about 14.5 billion years, which is called the Hubble time, and it is roughly the age of the universe. That is not a coincidence, and the near equality of the Hubble radius in light years and the age of the universe in years is the reason so many people conflate the two. So here is where we stand. The boundary is real, calculable, unmarked, and almost everything we can see lies beyond it. Which raises a question that has been sitting quietly underneath this entire conversation, and that I have deliberately not asked yet. If those galaxies are receding faster than light, how are we looking at them? Part 7. Then how are we seeing them? Let me stop and put the pieces on the table together, because we are halfway through and a lot has been dismantled. We started with an observation that sounds impossible. The majority of the objects in the sky are receding from us faster than light, and the number is not an exaggeration. It is a calculation from measured parameters. We looked at where the law came from and found a straight line drawn through scattered points by people who had no idea what they were building. We stated the picture that makes the observation feel like a violation, the detonation, the shrapnel, the pre-existing room, and we took away its center, its edge and its outside, one at a time, using nothing more exotic than 3 galaxies in a row and the evenness of the microwave sky. Then we read the speed limit properly and found that it is a statement about 2 things at the same place, and that the recession number is a sum of hundreds of small local nothings, none of which anybody performs. And then we located the boundary where that sum crosses the speed of light, and found it sitting 14.5 billion light-years away, unmarked, with 97% of everything we can see on the far side of it. So relativity is safe, nothing is broken, and if we stopped here, you would go to sleep reassured. Do not stop here, because there is a question underneath all of this that we have not touched, and it is much harder than the one in the title. If a galaxy is receding from us faster than light, if the distance between us is growing faster than light can cross it, then how does its light ever get here? Think about it as a race. The photon leaves the galaxy heading straight for us, traveling at exactly the speed of light through its own local space, which is the only speed it is capable of. Meanwhile, the space between it and us is being added to. And if the space is being added to faster than the photon can cross it, then the photon is losing, it is moving toward us, and it is getting further away, at the same time, forever. That should mean the light never arrives, not eventually, not after a long time, never. And yet the photographs exist. We have the spectrum of a galaxy at redshift 14.32. We have the spectrum of a galaxy at redshift 1090, from material now receding at 3.13 times the speed of light. And it is the most precisely measured thing in all of science. The light got here. It is getting here right now, continuously, from all of it. So this is the real paradox. The first one dissolved when we took away a bad picture. This one does not dissolve, because it does not depend on any picture. It is a straightforward consequence of things we have now established, and it appears to be wrong. Let me put you inside it. You are a photon. You have just left a galaxy, very early in the history of the universe, and you are aimed precisely at the location where the Milky Way will one day be. You are traveling at exactly the speed of light, which is the only thing you have ever done and the only thing you will ever do. Every local observer you pass measures you doing exactly c. Nothing about your journey feels like struggling, and the distance to your destination is increasing. Not because you have slowed, you cannot slow. You are covering ground at the maximum rate anything can cover ground. But between you and the place you are going, new distance keeps appearing, and it appears faster than you can eat it. So the gap grows. 1,000,000 years pass, and you are further from home than when you started. Another 1,000,000, and further still. You are moving toward the Earth at the speed of light, and moving away from the Earth at the same time, and both of those things are simply true. This goes on for a very long time. Hundreds of millions of years, in some cases billions. You are the fastest thing in existence, and you are losing. And then something changes, and it does not change because of anything you did. Here is the thing we did not say when we drew the Hubble sphere. It is not a fixed radius. Its size is the speed of light divided by the Hubble constant, and the Hubble constant is not constant. It is a rate, and it changes as the universe evolves. Through the long matter-dominated era, gravity was working against the expansion, and the rate was falling. And if the Hubble constant falls, then the speed of light, divided by it, gets larger. The Hubble sphere grows. It grows outward, and it grows faster than the struggling photon is receding. So at some point, the boundary sweeps over the photon's position. And once the photon is on the inside, the local recession rate where it sits is less than the speed of light, which means it is no longer losing ground. It starts to close. And from then on, the journey is uneventful. A long, slow, ordinary approach, over billions of years, at exactly the speed it has always been going. That is how the light gets here, not because anything outran anything, because the boundary moved. There is a classic problem that captures this, and it is worth doing properly because it makes the mechanism intuitive. Picture an ant at one end of a rubber rope, 1 kilometer long, crawling toward the far end at 1 centimeter per second. Every second, the entire rope is stretched uniformly by 1 kilometer. The ant is being outrun by an enormous margin. The far end is receding at 100,000 times the ant's speed. It should be hopeless. It is not hopeless. The ant arrives. It takes an absurd length of time, a number with tens of thousands of digits in it, but it arrives. And the reason is that the stretching is uniform. The rope behind the ant stretches too, and that stretch carries the ant forward. Every second, the fraction of the rope the ant has already covered stays put and grows with the rope. Only the fraction remaining has to be crawled. As long as the stretching is at a steady rate, that fraction always eventually reaches 1. Hold on to the words steady rate, because they are doing a great deal of work in that sentence. Change the stretching from steady to accelerating. Let the rope's length grow, not by a fixed kilometer each second, but by a fixed percentage each second. And the answer flips. Under exponential stretching, there is a critical distance. An ant that starts inside it arrives. An ant that starts outside it never does, no matter how long you wait, because the amount of rope being added ahead of it grows in step with how much rope there is, and it can never catch up. The problem stops having a solution. I am telling you that now because we are going to need it at the end of tonight, and because the universe changed which version of the problem it is running about 5 billion years ago, and nobody was consulted. But for most of cosmic history, the steady version is the one that applied. It is worth being concrete about why the Hubble constant was falling. In a universe whose contents are ordinary matter and radiation, gravity is the only thing with a vote, and gravity pulls inward. It does not stop the expansion. The expansion had too much momentum for that, but it does slow it. The rate at which any given pair of galaxies drifts apart, expressed as a fraction of their separation, decreases with time. And since the Hubble radius is the speed of light divided by that fraction, a falling fraction means a growing radius. For roughly 9 billion years, the Hubble sphere swelled outward through the universe, sweeping up photons that had been losing ground since before the first stars, and handing them a route home. But for the universe we have lived in so far, the rescue is real. The Hubble sphere grew, it overtook the photons, and they arrived. Which is why the Hubble sphere is not a horizon. A horizon is a boundary you cannot get information from. The Hubble sphere is a boundary that things routinely cross, from the outside in, because it is expanding across them. Every photograph of a high redshift galaxy is a photograph of light that spent part of its journey on the wrong side of that line and got in anyway. It arrived anyway. That is worth sitting with. Everything we know about the early universe, every measurement, every constraint on every parameter, comes from light that was, for a while, losing. And now, I want to show you the extreme case, because there is one photon in the story that lost worse than any other, and it is the one arriving in your room right now. Part 8. The Light That Lost Ground. The oldest light in the universe was released 380,000 years after the beginning. Before that moment, the universe was an opaque plasma. Electrons were free, not bound into atoms, and free electrons scatter photons relentlessly, so light could not travel in a straight line for any useful distance. It was like being inside a fog bank, or inside the sun. Then the temperature dropped through about 3,000 degrees. Electrons and nuclei combined into neutral atoms. The fog cleared in what was, on cosmic timescales, an instant, and every photon in existence was suddenly free to travel in a straight line forever. Those photons are still going. They have been stretched by the expansion from the orange glow of a hot furnace down into the microwave band, and they now correspond to a temperature of 2.725 degrees above absolute zero. They fill the entire universe, uniformly, in every direction. Several hundred of them are passing through every cubic centimeter of the room you are in. They are passing through your body right now, at a rate of billions per second, and they have been doing so continuously for your entire life. This is the cosmic microwave background, and it is the single most thoroughly measured object in the history of science, mapped by 3 generations of satellites to a precision of parts in 100,000. Nobody was looking for it when it was found. In 1964, 2 radio astronomers at Bell Laboratories in New Jersey, Arno Penzias and Robert Wilson, were trying to calibrate a horn-shaped antenna and could not get rid of a faint hiss. It was there day and night, in every direction they pointed, in every season. They checked the electronics. They suspected New York City and pointed away from it, and the hiss stayed. They found a pair of pigeons nesting in the horn, evicted them, cleaned out what Penzias delicately called a white dielectric material, and the hiss stayed. It took a phone call to a group at Princeton, who were at that moment building an instrument specifically to look for the radiation left over from a hot early universe, for anyone to realize what the noise was. What made it worse, historically, is that the prediction had already been made and forgotten. George Gamow, Ralph Alpha, and Robert Herman had worked out in the late 1940s that a hot beginning should leave a residual glow at a few degrees above absolute zero, and nobody had followed it up. Now let me tell you where it came from, and the arithmetic is simple enough to do out loud. That material sits, in the coordinates cosmologists use, 45.4 billion light-years from us today, but the universe has expanded by a factor of 1091 since the light left. So divide 45.4 billion divided by 1091 gives about 42 million. The material that emitted the particular microwave photons currently arriving at your location was, at the moment it emitted them, about 42 million light-years away. That is close. On cosmic scales, that is practically next door. About 17 times the distance to Andromeda. The universe was small, everything was compressed, and the stuff that made your microwave background was, in cosmic terms, just down the road. That same material is now 45.4 billion light-years away. And here is the number I have been building toward all night. At the moment it released that light, the material was receding from our position at 58.1 times the speed of light. That is, 58 times the speed of light. That figure comes from Davis and Lineweaver's calculation for a universe with 30% matter and 70% dark energy, which is close enough to the measured composition to be the standard answer. 58.1 C at emission, dropping to 3.13 C today. So think about what that photon did. It left, aimed at us, from 42 million light-years away, traveling at the speed of light, while the gap between it and us was opening at 58 times the speed of light. It did not stand a chance. It receded. It kept receding. Its distance from our location grew for a very long time, while it did nothing but travel toward us at the maximum rate the universe permits. And then the Hubble sphere caught up with it, and swept over it, and it began to close. And 13.8 billion years after it set out, it landed on a detector, on a satellite, at a point in space 1.5 million kilometers from Earth, and got turned into a number in a data file. It arrived anyway. I want you to hold that properly, because I think it is the strangest true thing in this entire subject. The most precisely measured signal in all of science, the foundation of modern cosmology, the thing from which we derive the age of the universe and its composition and its geometry, and the very Hubble constant we have been arguing about. That signal came to us from material that was outrunning its own light in our direction by a factor of 58. Every parameter in the standard model of cosmology is derived from photons that spent a substantial fraction of their journey moving away from the instrument that eventually caught them. The rule everybody knows and the sky everybody can measure have been sitting in apparent contradiction, in plain view, for 60 years. And the contradiction was never in the universe. It was only ever in the sentence. There is one more thing that makes this the strongest possible version of the argument, which is that the microwave background is not a marginal detection. It is the most perfect blackbody spectrum ever measured anywhere by anyone. When the COBE satellite spectrometer returned its result in 1990, the measured curve matched the theoretical shape so exactly that the error bars had to be drawn at 400 times their real size to be visible on the plot, and the audience at the American Astronomical Society meeting gave it a standing ovation. Deviations are constrained to below 1 part in 10,000. This is not a faint signal we are straining to interpret. It is the cleanest measurement in physics, and it came from 58 times the speed of light. Let me bring it forward to something with a name and a picture. In January of 2024, the James Webb Space Telescope pointed its near-infrared spectrograph at a faint smudge in a patch of sky in the constellation Fornax, and held it there for almost 10 hours. The object had been flagged in imaging as a candidate for something extremely distant, but candidates are cheap. Imaging can be fooled by a cool foreground star or a dusty galaxy at moderate distance, and the history of the field is full of record-breaking galaxies that turned out to be nothing of the kind. A spectrum is the proof. A spectrum shows you the actual features of the light and where they have moved to. When the spectrum came back, it was unambiguous. Redshift 14.32, with an uncertainty of plus 0.08 and minus 0.2. NASA announced it on the 30th of May, 2024. The object is called JADES GS Z140, and it is the most distant galaxy whose distance has been confirmed rather than estimated. The light left it 290 million years after the beginning of the universe. For scale, that is less than the time between the first dinosaurs and now. The galaxy is about 1,600 light-years across, which is small. Our own galaxy is 60 times wider, and it is roughly 5 times more luminous than the previous record holder, which is a problem in itself, because nobody expected galaxies that bright to have assembled that early. Its present distance from us is 33.8 billion light-years. Its recession velocity is 2.33 times the speed of light, and it was receding faster than light when it emitted the photons that Yost spent 10 hours collecting. Every object in that class has the same story. The deepest exposures we have ever taken are galleries of things that were, by any straightforward reading, unable to reach us, and reached us. There is a sting in this that I will save for the end, and it has to do with the fact that the mechanism which delivered all of these photons is not permanent, But before we get there, we need to look at what happened to the light itself on the way. Because a photon that travels for 13 billion years through an expanding universe does not arrive unchanged. It arrives stretched. And how you interpret that stretch turns out to determine what number you get for the velocity, which means the number in tonight's title is about to become less solid than it has looked so far. Part 9. The stretch that is not a Doppler shift. Every number we have used tonight traces back to one measurement, and it is worth being clear about what that measurement is and what it is not. We do not measure recession velocity. Nobody has ever measured the recession velocity of a galaxy. There is no instrument that does it, and there never will be. What we measure is redshift, and redshift is a comparison of two wavelengths, the one the light left with and the one it arrived with. We know the one it left with because atoms are the same everywhere. Hydrogen absorbs at the same wavelengths in a galaxy at the edge of the observable universe as it does in a laboratory in Geneva. So you find the pattern of lines in the spectrum. You notice it has slid toward the red end. You measure how far it slid, and you have Z. That is the observation. Everything else, the distance, the velocity, the age of the light, is computed from Z by feeding it through a cosmological model. The superluminal number in tonight's title is a model output. The model is extremely well tested, and I am not undermining it. But it is worth knowing which part of this is data and which part is inference, because in a moment, that distinction is going to matter enormously. So what does redshift mean in an expanding universe? The relationship is beautifully simple. 1 plus Z equals the ratio of the size of the universe now to the size of the universe when the light was emitted. That is the whole thing. If you measure Z equals 1, the universe has doubled in scale since that light left. If you measure Z equals 9, it has grown by a factor of 10. For Jade's GSZ 14.0, at Z equals 14.32, the universe has grown by a factor of 15.32 since those photons departed. Turn that around. When that light left, everything was 6.5% of its present size. Every distance in the universe was 15 times shorter. For the microwave background at Z equals 1090, the universe was 1/1091st of its present scale. The light stretched along with everything else. A photon that left with a wavelength of 1 unit arrives with a wavelength of 1 plus Z units. Ultraviolet light, emitted by hot young stars in the early universe, arrives here as infrared, which is precisely why JUICE is an infrared telescope, and Hubble largely was not, and why the record for the most distant confirmed galaxy jumped so dramatically the moment JUICE opened its eye. Notice something about that formula. There is no velocity in it, not hidden, not implied. It is a ratio of two sizes, and it has no upper bound whatsoever. There is no Z you cannot in principle have. Compare that to the Doppler shift you know. If a source is moving away from you through ordinary space, special relativity gives you a formula relating the redshift to the speed, and that formula is bounded. As the speed climbs toward the speed of light, the redshift climbs without limit. But the speed never reaches c. It cannot. The formula has c built into it as a ceiling. Now put those two side by side on the same object, and this is the comparison that I think makes the whole evening land. Take Jade's GSZ 14.0. Redshift 14.32. Feed that redshift into the special relativistic Doppler formula, as though the galaxy were an ordinary object moving away from us through ordinary space, and you get a velocity of 0.99151 times the speed of light, below the limit, comfortably. 99.15% of c, exactly the sort of number relativity is happy with. Feed the same redshift into the general relativistic cosmological calculation, and you get a recession velocity of 2.33 times the speed of light. Same galaxy. Same photograph, same 10 hours of telescope time, same single number coming off the spectrograph, 2.33 C or 0.9915 C, depending on which framework you asked. Neither number is a mistake. Both are correct answers to well-posed questions. They are simply different questions, and they have been given the same name. And here is why nobody notices. At small redshifts, the two calculations agree. At a redshift of 0.01, the Doppler answer and the cosmological answer differ in the fourth decimal place. At 0.1, they differ by a few percent. Astronomers routinely quote small redshifts as velocities by simply multiplying z by the speed of light, and for nearby galaxies, that is a perfectly good approximation and nobody is misled. The two frameworks only pull apart when z gets large. And for the first 60 years of extragalactic astronomy, nobody could see anything with a large z. The habit of calling redshift a velocity was formed in an era where the habit was harmless, and then the telescopes improved and the habit came along. You can watch this happen in the literature. Papers from the 1950s talk about the velocity of a galaxy without qualification. Papers from the 1990s start writing recession velocity, with the adjective doing quiet work. Modern papers on high redshift objects mostly avoid the word entirely and just quote the redshift, because the community learned the hard way that any velocity you print will be misread. When you see a press release that says a galaxy is receding at 98% of the speed of light, you are almost always looking at somebody who has applied the special relativistic formula to a cosmological redshift, because that produces a number that sounds impressive and does not sound impossible. It is not the number the cosmology gives. That is the moment where, for me, this stops being a puzzle about cosmology and becomes a puzzle about language. Somewhere in the 20th century, two quite different quantities ended up sharing the word velocity, and the speed limit attached itself to both of them in the public imagination, even though it only ever applied to one. But before we push further into that, I want to close off an escape route, because there is an obvious objection available, and it has a long history. Maybe the light is not stretched at all. Maybe photons just lose energy as they travel, some tiny interaction, some drag, some gradual leaching over billions of years, and what looks like expansion is nothing but tired light arriving exhausted. Fritz Zwicky proposed exactly this in 1929, in the same journal and the same year as Hubble's paper, and versions of it have circulated ever since, usually accompanied by the suggestion that cosmologists have not considered it. They have considered it. It is dead, and it was killed 3 separate times by 3 unrelated observations. The first is the cleanest. Type Ia supernovae are explosions with a characteristic pattern of brightening and fading, and the pattern takes a known number of days. If the universe is expanding, then a distant supernova should appear to unfold in slow motion, stretched in time by the same factor of 1 plus z that stretches the light. If the light is merely tired, there is no reason for the clock to change at all. Gerson Goldhaber and collaborators from the Supernova Cosmology Project published the test in the Astrophysical Journal in 2001. They took 35 of their own supernovae and 18 from the Callan-Tololo survey, applied the stretch correction and the 1 plus z correction, and every single light curve collapsed onto one common shape. The dilation parameter came out at 1.0, plus or minus 0.1, exactly the predicted value, and flatly incompatible with tired light. The Dark Energy Survey has since extended the confirmation cleanly out to redshift 1. The second is the blackbody spectrum we just talked about. Any process that scattered energy out of photons over billions of light years would blur the spectrum, because scattering is not perfectly gentle and it is not perfectly uniform. The microwave background is a textbook blackbody to better than 1 part in 10,000. Nothing has been interfering with those photons. The third is the Tolman test. The surface brightness of an object, how bright it looks per unit of apparent area, should dim as 1 over 1 plus z to the fourth power in an expanding universe, and it should behave completely differently in a static one. The measured dimming follows the expanding prediction. At redshift 10, that is a factor of about 14,600, which is a large part of why these galaxies are so hard to find. So the stretch is real. Something is genuinely happening to the light on the way here, and it is happening because the universe is bigger now than it was. But notice what survived that argument and what did not. The redshift survived. It is measured, it is invariant, and every observer everywhere agrees on it. The velocity did not survive. It split into two numbers that differ by more than a factor of 2. And if the velocity is that unstable, the next question almost asks itself, what about the distance? Part 10. When distance stops behaving. Ask how far away a galaxy is, and you expect one number back. In cosmology, you get 4. They are all correct, and they can differ from each other by more than an order of magnitude for the same object. The first is light travel distance, and it is the one that ends up in headlines. You take how long the light has been in flight and multiply by the speed of light. Jade's GSZ 140 emitted its light about 13.5 billion years ago, so its light travel distance is 13.5 billion light years, and that is the number you will see printed. It is not the distance to the galaxy, it is a duration, wearing the costume of a distance. It tells you when, not where. The galaxy did not stay put for 13.5 billion years waiting for its light to arrive. It went with the expansion, and where it is now is a completely different question. There is a giveaway that this number is not a distance, and once you notice it, you cannot unsee it. Light travel distance can never exceed the age of the universe in light years. It is capped at 13.8 billion by construction, because nothing has been traveling longer than that. Which is why every record-breaking object announced in the last 20 years has been reported as roughly 13.3, then 13.4, then 13.5 billion light-years away, creeping toward a ceiling. The galaxies got dramatically further apart with each new record. The published number barely moved, because the published number was measuring time. The second is co-moving distance. Imagine a grid laid over the universe that expands along with it, so that galaxies sit at fixed grid coordinates and never move on the grid at all. Co-moving distance is the separation measured in grid squares, with the expansion divided out. It is the natural coordinate for cosmology, because it does not change with time for objects that are just going along with the flow. The third is proper distance, which is the honest physical one, how far away the thing is right now, if you could freeze the universe at this instant and lay out rulers. For a flat universe at the present moment, proper distance and co-moving distance happen to coincide, which is a convenience. For Jade's GSZ 140, that number is 33.8 billion light-years, not 13.5, 33.8, which is 2.5 times larger, and it is the number every recession velocity tonight has been computed from. And then there is the fourth, and this is where things stop making sense. Angular diameter distance is the distance you infer from how big something looks. It is the most intuitive kind of distance there is. It is how your eyes work. Something twice as far away subtends half the angle. Hold your thumb at arm's length. Move it to twice arm's length. It looks half as wide. You have relied on this every waking second of your life. In this universe, it stops working. The angular diameter distance increases as you go out, exactly as intuition demands, all the way to a redshift of about 1.59. At that point, it reaches a maximum of 1,794 megaparsecs, about 5.85 billion light-years, and then it turns around and starts to decrease. Past that redshift, more distant objects subtend larger angles on the sky. They look bigger the further away they are. The The reason for the turnover is the same physics we have been circling all night. Those objects were receding superluminally when they emitted their light, which means the light left at a moment when they were physically very close to our location. The angle a thing subtends is set by how far away it was when the light departed, not by where it has drifted to since. Push far enough out in redshift and you are looking at emission events that happened when everything was crushed together, and the angles reflect that closeness. Let me make that concrete. Take two identical galaxies, put the first at a redshift of 1.5, and it behaves. It looks small, and if you pushed it further, it would look smaller, and everything is fine. Now take the second and put it at a redshift of 10, nearly 7 times further in redshift, 3 times further in co-moving distance, so far away that its light left before the universe had made most of its stars. It is dimmer by a factor of many thousands. It takes a space telescope hours of accumulated exposure to register at all. And it is physically larger on the sky than the closer one. Not by a huge amount, but measurably, unambiguously larger. You are looking at an object that is fainter by 4 orders of magnitude and wider in angle at the same time. Its apparent size has nothing to do with how far away it is now. Its apparent size was fixed at the moment the light left, when the entire configuration, that galaxy, the space between, the material that would become you, was compressed into a region 11 times smaller in every direction. You are seeing an angle frozen from a moment when the universe was close enough that the thing genuinely was nearby. Push it all the way, and the effect becomes absurd. At the surface of last scattering, the angular diameter distance has collapsed to about 13 megaparsecs. 13. That is closer than the Virgo cluster. The microwave background, in the specific sense of how large things on it appear, is behaving like something 40 million light-years away. And that fact is not a curiosity. It is the entire basis of how we measure the geometry of the universe. The characteristic size of the hot and cold spots is known from physics, the angle they subtend is measured, and comparing the two tells us space is flat. That measurement runs directly through the angular diameter distance, turnover and all. The dimming, meanwhile, is savage. Surface brightness in an expanding universe falls as 1 over 1 plus z to the 4th power, 4 powers, because 2 come from the energy of each photon being reduced, and the rate of their arrival being reduced, and 2 more from the geometry. At redshift 10, that is a factor of about 14,600. At redshift 14, it is closer to 50,000. This is why finding these objects requires a telescope in a cold orbit 1.5 million kilometers from Earth, with a mirror 6.5 meters across, and why the field spent 30 years waiting for one. So we have 4 distances. The light travel one says 13.5 billion light-years. The proper one says 33.8. The angular one says the thing looks like it is about 2.2 billion light-years away. All 3 are correct answers to different questions, and only one of them was used to compute the recession velocity that gave this video its title, which is the last piece of the pattern, and by now you can probably see the shape of it. The redshift is the thing everybody agrees on. Every quantity we derive from it, the distance, the velocity, the size, the age, depends on choices about how to slice the universe up and which question to ask. The observation is solid. The interpretation is where the drama lives. And before we go all the way into that, there is one more thing to look at, because if superluminal recession is a normal consequence of an expanding universe, then there was an era when it was not merely normal, there was an era when it was the whole story. Part 11. The fastest the universe ever went. Everything we have discussed so far has involved recession velocities of 2 or 3 times the speed of light. Those are the numbers you get from the universe, as it has been for most of its life, expanding gently, at a rate that halves the density every few billion years. There was a period, when it was not gentle. Come with me to a moment less than a trillionth of a trillionth of a trillionth of a second after the beginning. 10 to the minus 32 seconds. There is no useful way to picture that interval. Light in that time crosses a distance far smaller than a single atomic nucleus. Hold 2 points in mind, separated by less than the width of a proton, close enough that a signal could have passed between them a moment earlier. Now the interval between them opens by a factor of at least 10 to the 26, 100 trillion times, in less time than light needs to cross a nucleus. That is inflation, and the recession velocities involved make 3 times the speed of light look like a rounding error. 2 points that could have exchanged information a moment ago are now, permanently, out of contact with each other. Everything you will ever see, every galaxy, in every image ever taken, was inside that patch when it started. And here is the structural point that I think matters more than the numbers. Inflation was not something cosmologists were forced to accept. Nobody found evidence of superluminal early expansion and then reluctantly worked out how to live with it. Inflation was invented, deliberately, as a fix, because a period of enormous superluminal expansion solves problems that nothing else solved. The first is the horizon problem. Patches of the microwave sky on exactly opposite sides of us have the same temperature to 1 part in 100,000. Under ordinary expansion, those patches have never been in causal contact. Nothing could have passed between them, ever, so there is no mechanism by which they could have come to the same temperature. Inflation fixes it by having them in contact before inflation, in thermal equilibrium, and then flung apart faster than light. The second is the flatness problem. The geometry of space is measured to be flat, to within a few parts in 1,000, and flatness is unstable. Any small deviation grows with time, so a universe that is nearly flat now must have been absurdly, implausibly flat at the beginning. Inflation fixes it by stretching whatever curvature existed until it was undetectable, in the same way that any curved surface looks flat if you magnify it enough. It is worth saying that inflation is not confirmed in the way the microwave background is confirmed. It is the leading framework, and it has survived 30 years of precision tests, but the direct fingerprint, a background of gravitational waves generated by the inflating field, which would leave a particular twisted pattern in the polarization of the oldest light, has not been found. The quantity that measures it is called the tensor-to-scalar ratio, and the combined limits from the BICEP experiments at the South Pole and the Planck satellite put it below 0.036. Instruments now being built aim to push that down by another factor of 30. If they find it, inflation is essentially proven. If they do not, the picture stays plausible and unconfirmed, and the number of E-foldings stays a lower bound rather than a measurement. Nobody in that process worried they were breaking relativity. There was nothing to worry about. Even at 10 to the 26, the word is local, and locally nothing moved. Every point stayed put in its own neighborhood, doing nothing, while the amount of distance between neighborhoods grew. Which brings up the question you have probably been holding since the first part, and I want to answer it honestly rather than leave it hanging. If space can be made to expand faster than light, can we use that to travel faster than light? The idea is not silly, and it is not fringe. In 1994, a Mexican physicist named Miguel Alcubierre published a paper in Classical and Quantum Gravity titled The Warp Drive, Hyperfast Travel Within General Relativity. It is a real solution of Einstein's field equations. The construction contracts space in front of a bubble and expands it behind, so the bubble as a whole moves superluminally relative to distant observers, while a ship inside it never locally exceeds the speed of light, sitting in flat space the whole time, feeling no acceleration. The logic is borrowed directly from cosmology, and it is borrowed correctly. So why can we not build one? Not because of the speed limit, That is the point worth taking away. The obstacles are entirely different. The solution requires a large quantity of negative energy density, which violates the classical energy conditions, and for which no macroscopic source is known to exist. Alcubierre's original estimate for the energy required was catastrophic. Chris van den Broek showed in 1999 that changing the bubble's geometry cuts the requirement by an enormous factor, and Alexei Bobrik and Gianni Martire reframed the whole family of solutions in 2021 and found that every physically reasonable member is subluminal. There is a horizon problem inside the bubble. The interior is causally disconnected from the leading edge, which means a ship inside cannot send a signal forward to steer or stop it. You would have to set the whole thing up in advance, along the entire route, which rather defeats the purpose. There is a debris problem. Particles swept up by the front of the bubble accumulate against it and are released at the destination with catastrophic energy. And then there is the one that is genuinely fatal, which is causality. Any device that carries information along a space-like path, combined with a second such device in relative motion, allows a signal to be sent into the sender's own past. This was worked out in 1970 by Benford, Book and Newcomb, who called the resulting device a tachyonic anti-telephone. It is not a technical difficulty, it is a logical one. So the honest answer to the question is no, and the reason is not the one you would expect. Cosmic expansion does not break the speed limit, so it cannot teach us how to break it. It works precisely because nothing anywhere is going anywhere, which is a reassuring place to be. And I would leave you there, except that we are not finished, because the resolution we have built over the last 2 hours is itself still being argued about by people who agree on every single number. Part 12. The argument physicists are still having. I have spent most of tonight telling you that space expands, that galaxies sit still while the distance between them grows, and that this is why the speed limit is untroubled. That account is standard. It is what you will find in most textbooks, and in essentially every popular treatment. A significant number of professional cosmologists think it is a bad way to describe what is happening, and they have been saying so in print for decades. In 2009, Emery Bunn and David Hogg published a paper in the American Journal of Physics called The Kinematic Origin of the Cosmological Redshift. Their claim is that the standard story has it backwards. The cosmological redshift, they argue, is most naturally understood not as light being stretched by growing space, but as an ordinary Doppler shift, or rather, as the accumulation of an enormous number of very small, ordinary Doppler shifts, added up along the photon's route. Here is the construction, and you will recognize the setup because we built it in the 5th part of tonight's script. Take the chain of co-moving observers strung out between a distant galaxy and us. The photon leaves the galaxy and immediately passes the first observer in the chain. That observer is moving very slightly with respect to the source, so they see the photon slightly redshifted, an ordinary special relativistic Doppler shift, at a tiny relative velocity, entirely covered by the old theory. The photon carries on and passes the second observer, who is moving slightly relative to the first, and picks up another tiny Doppler shift, and another, and another. Hundreds of millions of infinitesimal handoffs, each one perfectly ordinary, each one obeying the flat space formula exactly, because in each small patch, space-time is flat, and the flat space formula is exact. Multiply all those tiny shifts together, and you get the cosmological redshift. Precisely. No stretching required. Nothing had to happen to the photon along the way. It simply passed through a succession of observers who were, each with respect to the last, moving a little. Their complaint about the stretching space picture is not that it gives wrong answers. It does not. It is that it obscures the central lesson of relativity, which is coordinate freedom. No description is privileged. When you say space expands, You are stating a property of one particular coordinate system, and by treating it as a physical event, you teach people that the coordinate system is real. The other side answered. In 2007, Matthew Francis, Luke Barnes, Berrien James, and Geraint Lewis published a paper in Publications of the Astronomical Society of Australia with the title, In Complete Earnest, Expanding Space, the Root of All Evil. Their answer is no. Expanding space is a valid framework for describing how the whole solution evolves, and the arguments against it fail because they attribute physical properties to expanding space that general relativity never gave it. Expanding space does not drag anything. It has no substance, exerts no force, has no local presence, and cannot be detected by any local experiment. If you strip all that out and keep only what the mathematics says, the framework is legitimate. And the argument is still running. Lewis and colleagues returned to it in 2016 with a paper asking, once again, whether space really expands. You can see the stakes of the disagreement most clearly in the questions students ask, which are the questions you have probably asked yourself. Does the space inside an atom expand? Does the space between the Earth and the Sun expand, just a little, and get pulled back by gravity? Is there a tug-of-war going on inside every solid object, expansion pulling outward, and electromagnetism holding on? Under the stretching picture, those questions sound reasonable and require careful answers about competing effects. Under the kinematic picture, they do not arise at all, because there is no stretching agent to compete with anything. Two atoms in a molecule are not co-moving observers drifting apart. They are bound, they share a local frame, and the cosmological description simply does not apply to them. The answer under both accounts is the same. Nothing happens. There is no residual pull. Bound systems are entirely unaffected. But one of the two pictures generates the confusion in the first place. Sir John Peacock, one of the more prominent voices on this, has argued in print and in lectures that the rubber sheet analogy has caused more student confusion than any other single teaching device in cosmology. There is a second question with the same shape. When a photon redshifts, its energy drops. A microwave background photon arrives with about 1,000th of the energy it left with. Where did the rest go? Under the stretching picture, the question feels urgent and unanswered, and people reach for explanations involving work done against expanding space. The technically correct answer is that energy conservation, in the form you learned it, is a consequence of the laws being unchanging in time, and in a universe whose geometry is evolving, that condition does not hold globally. There is no global energy conservation law to violate. The question is malformed, and the stretching picture is what makes it feel well-formed. Now hold both camps in mind and notice what they are not disagreeing about. They make identical predictions. Every one. There is no observation that distinguishes them, no experiment that could be run, no measurement that would settle it. They are two descriptions of the same mathematics, and the mathematics has never been in doubt. Which tells you exactly where this whole evening's paradox has been living. It was never in the universe. It was in the words. And there is one example that makes this so clean it is almost brutal. Consider a universe with nothing in it. No matter, no radiation, no dark energy. Completely empty, with test particles flying apart from a common origin. This is called the Milne universe, and it has been studied since the 1930s. Write it in the standard coordinates that cosmologists use, the co-moving coordinates we have been using all night, where galaxies sit at fixed grid points, and the grid inflates. In those coordinates, the Milne universe expands. Its scale factor grows in direct proportion to time. It obeys Hubble's law exactly. It has a Hubble sphere, and it contains co-moving observers whose recession velocities exceed the speed of light and, as you go further out, run away to infinity. Now change coordinates. The Milne universe is flat, empty Minkowski spacetime. It is the space-time of special relativity, nothing else. It is the ordinary flat arena of a first-year textbook, sliced up in an unusual way. Write it in the ordinary coordinates, and every one of those observers is an ordinary object moving at an ordinary sublight velocity, and the infinite recession velocities are not reduced or reinterpreted. They are gone. They do not appear anywhere in the description. Nothing physical changed. Not one thing. No particle moved differently. No clock ticked differently. No photon took a different path. All that changed was which family of surfaces you decided to call moments of constant time, and a quantity that can be made infinite or made to disappear by relabeling the same events is not a property of the universe. That is the sentence I would like to leave in your head from this part. The number in tonight's title, 2.33 times the speed of light, 3.13 times the speed of light, 58.1 times the speed of light, is not something the universe possesses. It is something a coordinate system possesses. The universe does not have a fact about how fast that galaxy is receding. We have a convention, a good one, a useful one that makes the equations tidy and lets us build tables and compare surveys. And under that convention, the number comes out greater than the speed of light. Nobody is moving, and now the sentence has a second meaning it did not have before, because it turns out there is not even a fact of the matter about how fast they are not moving. If you want a smaller and more familiar version of the same lesson, flat spacetime will give you one. An observer who accelerates steadily through completely empty, completely flat space, no gravity, no curvature, nothing at all, acquires a horizon behind them. There is a surface from beyond which no signal will ever catch up with them, for as long as they keep accelerating. It is called a Rindler horizon, and it is as real to that observer as any horizon in cosmology, and it does not exist for anybody who is not accelerating. Same spacetime, same events. A horizon for one observer and no horizon for another. Horizons, like recession velocities, turn out to be features of a point of view. I want to add one caution, because there is a way to overlearn this lesson and end up somewhere wrong. It would be easy to conclude that expansion is purely bookkeeping and nothing real is happening at all. That is not right either, and there is a thought experiment that shows why. Tamara Davis, Charles Lineweaver, and John Webb published it in the American Journal of Physics in 2003, and it is called the tethered galaxy problem. Take a distant galaxy and imagine tethering it to us with an unbreakable cable, holding it at a fixed proper distance so it is not receding at all. Now cut the tether. What happens? In a decelerating universe, the galaxy drifts toward us. In an accelerating universe, it drifts away. The answer depends on the actual dynamics, which means there is something physical here that the coordinates do not get to decide. Expansion is not a force, and nothing is being dragged, but the rate of expansion is changing, and change of rate is acceleration, and acceleration is real in a way that velocity is not. Which leaves us with exactly one thing in this story that is unambiguously, coordinate independently, physically real. And it is not the number in the title, it is what the acceleration is doing. Part 13. What the question was really asking. So here is the answer, plainly, with nothing held back. The universe can expand faster than light because the thing we are calling faster than light is not a velocity. The speed limit in relativity is a rule about two objects at the same place. It says that if you and something else are at the same event, your relative speed cannot reach the speed of light. It has never said anything about how fast a distance can grow between two objects that are far apart, each sitting quietly at rest in its own neighborhood, connected by a chain of hundreds of other objects that are also sitting quietly at rest. That growth rate is a sum. It is a sum of small local nothings. and a sum is not a thing anybody does. Nothing in the universe has ever outrun light, anywhere, at any moment, in any place, where the phrase would mean something. The word is local. That single adjective, dropped from the 6-word version everybody learns, is the whole answer. And nobody is moving. Not the galaxy at redshift 14, not the material that made the microwave background, not us. The galaxies are exactly where they have always been, and the amount of distance between them has increased, and if you insist on dividing that increase by time and calling the result a speed, you will get a number bigger than the speed of light, and it will be a number about your coordinate system, not about the universe. That is the answer. It is not a loophole, and it is not physicists quietly relaxing a rule they could not defend. The rule was always narrower than the slogan. From the first paper Einstein wrote about it in 1905, and the confusion is entirely a translation error between the physics and the English. I would like to leave you there, because it is a comfortable place to end, but there is something underneath it, and it does not go away when the paradox does. Go back to the mechanism that saved the light. Every photon that has ever reached us from beyond the Hubble sphere, which is to say, essentially every photon that carries information about the early universe, arrived because the Hubble sphere grew and swept over it. That growth happened because the expansion rate was falling, and the expansion rate was falling because gravity was pulling against the expansion. In 1998, 2 competing teams of astronomers, one led by Saul Perlmutter and one by Brian Schmidt and Adam Rees, were measuring distant supernovae in order to work out how fast the expansion was slowing down. Both teams found that it is not slowing down. It has been speeding up for roughly the last 5 or 6 billion years. They shared the Nobel Prize for it in 2011, and nobody has a satisfying explanation for the cause, which we call dark energy, mostly as a placeholder for our ignorance. Here is what acceleration does to the story we have just told. If the expansion accelerates, the Hubble constant does not fall to 0. It approaches a fixed value and stays there. And if the Hubble constant stops falling, then the speed of light divided by it stops growing. The Hubble sphere stops expanding, which means it stops sweeping up photons. The rescue mechanism that delivered every image in every long exposure survey, every measurement of the early universe, every constraint on every parameter in cosmology, that mechanism is switching off. It has been slowing for billions of years, and it is heading for a halt. Remember the ant on the rubber rope. Under steady stretching, the ant always arrives, no matter how badly it is outmatched. Under accelerating stretching, there is a critical distance, and an ant outside it never arrives, no matter how much time you allow. The universe stopped running the first version of that problem about 5 billion years ago and started running the second, and nobody was consulted. When the Hubble sphere stops growing, it settles onto a second boundary, one we have deliberately not discussed until now. That boundary is the cosmic event horizon, and it sits at about 16 billion light-years in co-moving distance, drifting out toward perhaps 17 or 18, and then stopping. Light emitted right now from anything beyond it will never reach us, not in 100 billion years. Not ever. There is no mechanism left to bring it in. Here are the numbers, and this is the part that stays with you. Any galaxy we currently observe at a redshift above roughly 1.8 is, at this moment, emitting light that will never arrive here. We can see it. We have its photograph. We are looking at photons it sent long ago, and those photons are still coming, and will keep coming for a very long time, arriving ever more redshifted and ever fainter. But whatever is happening there tonight is already outside the story. We will never know. Between 94 and 96% of the galaxies currently visible in our sky are already in that category, already beyond reach, already beyond signaling, already permanently out of contact, not because they are too far to travel to, but because the geometry has closed. Their images will keep arriving, redshifting toward infinity, dimming toward nothing, freezing at the horizon like a paused film. And what they are actually doing, we will never learn. It is worth being precise about the difference between the two boundaries, because we have now used both, and they are easy to run together. The Hubble sphere, at 14.5 billion light-years, is where recession velocity equals the speed of light. Things cross it, from the outside in, and their light gets here. The event horizon, at about 16 billion co-moving light-years, is where light emitted now stops being able to reach us at all. The Hubble sphere is a line in a calculation. The event horizon is a line in the causal structure, and it is the one that matters. For most of cosmic history, the Hubble sphere was inside the event horizon and growing toward it. Now it is nearly there, and when it arrives, the two become the same thing, and the era of light, arriving from beyond, ends. There is a further consequence that I find harder to sit with than the loss of the galaxies. It is the loss of the evidence. Lawrence Krauss and Robert Scherer wrote a paper in 2007 with the title The Return of a Static Universe and the End of Cosmology, and the argument is straightforward. Everything we used to work out the history of the universe, the recession of distant galaxies, the microwave background, the abundances of light elements in pristine gas that has never been through a star, is temporary. The galaxies go past the horizon. The microwave background redshifts until its wavelength is longer than the observable universe and becomes undetectable. The pristine gas gets processed. Give it 100 billion years, and the observational basis of cosmology is gone, not hidden, gone. And the correct scientific conclusion available to anyone living then will be a static, eternal, single galaxy universe. They will do good science and get the wrong answer, and there will be no way for them to know. That is the reversal I want to leave you with. The thing that sounded frightening, expansion outrunning light, the speed limit apparently in ruins, the universe breaking its own most famous rule, turned out to be nothing. A category error, a word doing two jobs. There was never anything wrong, and the thing that sounds harmless, a slow, quiet, imperceptible acceleration, a number drifting by a fraction of a percent per billion years, something you could not detect in a laboratory if you had 1,000 lifetimes, is taking the universe away, not violently, not dramatically, just steadily, and permanently, and it has already taken most of it. The light from the microwave background arrived anyway. It came to us from material receding at 58 times the speed of light, and it lost ground for a very long time, and it got here regardless, and everything we know is built on it. From now on, for almost everything out there, it will not. There is one more thing worth saying, and it is not entirely bleak. We are living in a peculiar and privileged window. There was a time, early on, when the universe was too hot and too opaque for any of this to be visible. There will be a time, very far ahead, when the accelerating expansion has carried everything beyond the horizon, and an astronomer will look up and see only the stars of their own merged galaxy, with an empty black sky behind them, and no way whatsoever to discover that anything else ever existed. They will have no expansion to measure, no redshifts to plot, no microwave background to detect. They will conclude, reasonably and completely wrongly, that their island of stars is the whole of creation. We are in the narrow band in between, when the evidence is still arriving, when you can point a telescope at a smudge in Fornax and pull 13.5 billion years out of it, when the oldest light in existence is still falling on us from all directions, all the time, including on your closed eyelids right now. And one last note, because the story may not be finished. The DESI survey's second data release, in 2025, reports a preference for dark energy that changes with time rather than staying constant, at a significance somewhere between about 3 and 4 sigma, depending on which supernova sample you fold in. If that holds up, and it is not yet settled, then the acceleration may weaken. The horizon may not close the way we have described, and some of what we have written off may still be reachable. We do not know. It is one of the most consequential open questions in physics, and it may be resolved within a decade. So the next time you see one of those photographs, the field of scattered light with thousands of galaxies in it, you can hold the whole of it at once. Almost every object in the frame is receding from you faster than light. Not one of them is moving. The light should never have arrived, and it did. And the answer to how the universe can expand faster than light is that it never has, because that was never what the words were describing. Nobody is moving. It only ever looked that way from here.